So the two kinds of spectroscopy that we kind of talked about yesterday, really we only talked about one type, honestly. And that was really the X-ray spectroscopy, okay? So I want to talk about a couple other ways that spectroscopy can be used. And basically, all we're talking about when we say spectroscopy is we're hitting matter with light, with electromagnetic energy, and we're seeing what happens to it, okay? We're kind of measuring what occurs. So with the X-ray, it's called XPS, or you can have UPS as well, if you really want to package. Anyway, sorry, that was a bad joke. I shouldn't have made it. We only have 20 minutes. So XPS is basically you shoot X-rays at this surface, and you see how the electrons are ejected out of it. Because when you hit something with X-rays, you're going to kick electrons out, because that's really high energy radiation, right? You guys remember how the electromagnetic spectrum kind of goes? So the highest energy radiation is gamma, right? Think the Hulk, right? That's how the Hulk was created. If that really happened. It did. Anyway, so gamma radiation, right, is the most intense electromagnetic radiation, the highest energy electromagnetic radiation. X-rays is just one step down from that, okay? So you hit something with an X-ray, you're giving it a lot of energy, right? And that's enough energy to break those bonds between the electrons and the protons inside the atom, and the electrons come shooting off, okay? Now, infrared, where does that fall in the spectrum? It's actually, well, depending on which direction you're going. If you're going high to low, then it's right after the visible. You're right. So it's a little bit lower energy than the visible spectrum, right? Okay? And so, well, it's right here, I guess. But if you've got your visible light spectrum, it's called infrared because it's just a little below red as far as the energy, right? I don't know why they turned it this way instead of having it flipped around. Usually we read things left to right, but whatever. So you can see here, you've got the red end of the spectrum. That's the lowest energy visible light, and then you've got infrared. Now we can't see infrared radiation unless you're wearing something like night vision goggles, right? But things that give off heat give off infrared radiation, and that's why the night vision goggles work. You can actually see the heat that's coming off of people. Ultraviolet is on the other end, so you've got violet in the visible spectrum, and then ultraviolet, a little bit higher than violet, okay? And that's a little bit higher energy than visible. So when we're talking about infrared spectroscopy, do you think that's going to be able to knock electrons out of an atom? Probably not, okay? It's too low energy to really eject electrons out of something. I don't know if you guys remember the photoelectric effect, but one of the things they realized is it's kind of, the division right here is right somewhere in the middle of visible light, where this color light over here, this energy of light, is not enough to really eject electrons out of something, okay? You get over here towards the blue and the violet end of the spectrum, now you can eject electrons out. So this is kind of the cutoff right in the middle of the visible spectrum, okay? So infrared is not going to be able to eject electrons. But we can use infrared radiation for something else. Yeah, this looks complicated, right? We're not going to talk about all of this, okay? I just want to introduce you to this right now. But the idea here is, with infrared spectroscopy, you hit a molecule of some sort with infrared radiation, and you can actually get these vibrations from the bonds within that molecule. This is done a lot with organic molecules, long carbon-hydrogen chains, that sort of thing. A double bond will vibrate a little bit differently than a single bond, which will vibrate a little bit differently than a triple bond, right? So you can actually kind of get a fingerprint for this chemical based on the way, the vibrations it gives off when you hit it with infrared light, okay? And basically it's measuring the absorptions of that light, because it will absorb the infrared light when the vibrations match up, okay? So you get a certain energy infrared, it's going to absorb that energy if you have maybe a double bond, where it wouldn't absorb that energy if you have a single bond, okay? So you get these unique fingerprints here, okay? And basically you get spikes at certain places, and it shows, okay, that's where it's absorbing the light, in these particular places. You can, if you have a known chemical, you can kind of lay that over an unknown, and if it matches up, well, there's your chemical. This is like a chemical fingerprint, right? So it's a way to help identify an unknown compound. Is a really useful way to use this. It also just gives us really good detailed information about what's going on within the bonds. So this has helped us to validate some of our atomic theory that we're going to get into in the next few days. It's helped to kind of show us, yeah, I think we're on the right track here, okay? So that's infrared spectroscopy, just a very brief, quick introduction to it, all right? The other type is just UV visible spectroscopy, okay? And this is going to be high enough energy to eject an electron, but there's another way that this can be used. Really, XPS is better for ejecting electrons. Let me show this to you. Visible UV spectroscopy. This is really useful when you have a colorful solution that gets created, and you want to measure the concentration of it. Okay, that's what we're going to use it for in a lab that we'll do either next week or the week after that. I can't remember. Okay, but you can actually measure, based on the color, you can measure the absorption of certain wavelengths of light, and that can actually, if you use a formula called Beer's Law, you can actually, Beer's Law. It's technically called the Beer-Lambert Law, but it's shortened to Beer's Law all the time. I'm not sure. But the idea here is you can actually measure the concentration of a solution based on how much of a specific type of light that it absorbs. Okay, and so we're going to do a lab on that. And again, most of this stuff is way more complicated than we need to get into. But I put these two links on your activity just because I wanted you to be able to kind of get an idea of what these things are. Okay, I did not find the simplest way to explain these. I just found some that I felt like did a decent job of introducing the concept. I was trying to find ones that were pretty short because some of the other ones were like 100 pages long, and I didn't want you to have to wade through all that. So I was trying to look for fairly short ones. Okay. But basically, all of this, and this gets into, see here you can see in a little more complicated format. This is talking about what we talked about last year, where electrons are jumping energy levels and they're exposed to certain types of radiation. Okay, but this kind of gets into molecular orbital theory, which we're going to talk about very briefly, but we didn't talk about it at all last year. Okay. So don't worry about the bonding, the anti-bonding, and all these weird pies with asterisks and stuff like that. That's fun stuff that you get to do if you go on in college chemistry. And then it talks about conjugation. You really probably don't need to do anything with that yet either. Again, I'm probably just scaring you with all this stuff, but what I'm trying to show you right now is I want you to get the big idea that this is really all just, it's all kind of the same thing, right? So whether you're hitting it with X-rays or UV or visible light, or you're hitting it with infrared radiation, you can use those in different ways to be able to figure out some of the characteristics of the substance that you're hitting with the light, okay? And that's always been a way that we've been able to observe things, right? You see how the light reflects off of it. You see how light gets absorbed by it, and you're able to tell some of the characteristics of substances. We're just doing it for very, very small things that can't normally be seen with the human eye, okay? So that's the idea. So again, just a quick wrap up here. XPS, it's going to be best used in situations where you actually want to eject the electrons and you want to sort of be able to tell the internal structure of the atom itself, okay? The infrared is going to be best used when you're trying to figure out maybe the structure of the bonds in a molecule, or if you're looking for a chemical fingerprint trying to identify an unknown. Okay. UV visible is often used. Now, all of these can be used for other things. I'm just giving you general categories here. UV visible spectroscopy is often used to measure concentrations of solutions, especially when there's a color to them. Doesn't have to be a color necessarily in order for this to work, but it works best with colorful compounds. Okay? So that's just kind of a good, broad overview. And the reason that I'm telling you all this is because this is specifically an objective in the new AP course. They want you to be able to justify the selection of a particular type of spectroscopy in order to measure properties associated with molecules. Okay? And vibrational, when you see vibrational, you should probably be thinking infrared. Okay? When you see electronic motion of molecules, you should probably be thinking either UV visible spectroscopy or X-ray. Okay? So that's basically, I think that's what they want you doing. So this activity basically just goes through some scenarios, right? And it's asking you which one of these types of spectroscopy do you think would be the best for that particular situation. Okay? So how much time do we have left here? 10 minutes? Okay. So we have time to go through some of this one. This is the main one that I wanted to get through today. 5 minutes. Awesome. Okay. But this won't take very long, all right? So let's go through a few of these scenarios and see if we can figure out which would be best in that situation. So a student wants to identify a set of samples based on the color they burn when put into a flame, okay? Now, when we say color, that's a big hint, right? Because when we see color, what are we actually seeing? We're seeing visible light. We're seeing light in the visible spectrum, right? So we're probably talking, if we're looking at the color something burns and we're trying to separate those colors out with a spectroscope, then we're probably talking about UV visible, okay? So that would be UV vis spectroscopy. Number 2, a lab technician would like to identify an unknown sample without destroying or altering the surface of the material. So identification. Any thoughts there? Okay. Remember, one of the things that I said was that infrared is pretty good at helping to identify unknowns. Okay. Now, these are not always cut and dry. An argument could be made for using, well, X-ray does a little bit of damaging to the surface of the material. It's not a high amount. Okay. But an argument could be made for maybe UPS or XPS, ultraviolet or X-ray in this case. Ultraviolet especially really doesn't damage the surface of the material at all. Once you get up to higher energy like X-ray, there's a little damage, but it's very minimal. Okay? Just don't hit it with gamma radiation. Okay, so student wants to obtain data about the core, the inner electrons of the atoms on the surface of a known material. But she needs to obtain data for some of the atoms below the surface as well. Yeah. Okay, that would be X-ray, right? Because we need some high energy radiation that's going to penetrate down into, below the surface of that material and knock out some of those inner electrons that are there. Okay? By the way, I don't think I said this. This would be a good thing to say. UV visible light typically messes more with the outer, the valence electrons. Okay, if you want to mess with the core electrons and actually eject some of those, you're probably going to have to use X-rays because they have a much higher energy. They can get into the atom and knock some of those electrons with higher binding energies off of the atom. Okay? Lab technician is only interested in obtaining data about the valence electrons. Well, I just helped you out with this one, I think. On the surface of a known solid. He also wants to make sure the surface of his material is not damaged in any way during the process. Well, that one, see, again, if we're wanting to find data about the valence electrons, we probably have to knock the valence electrons off, right? Remember, well, okay, yeah, so you're right. We don't want to damage it in any way, but the only one that really does much damage is the X-ray, okay? So as long as we stay away from the X-ray, we're probably okay. That one, probably the best choice would be the UV visible spectroscopy on that one, because then you're still going to knock off those valence electrons, but you're not going to do any damage really to the surface of the material. Okay. All right. There's a few other questions there. I think we're pretty much out of time, but hopefully you kind of get the idea. And I will post the answer key to this on Moodle so you can check your work. Okay. All right. Good class, everybody.